Hi everyone, my name is Willy Vasquez, and today I'll be telling you about this work that's done jointly with Stephen Checkoway of Oberlin College and Hovav Shacham of UT Austin. So in the brief time that I have for this talk, I'll introduce the complexity of video decoding and demonstrate the decoder attack surface. Then I'll show you H.264 Forge, a toolkit to produce specially crafted videos to find vulnerabilities in video decoders and investigate their exploitability. And finally, I'll provide an overview of an iOS kernel denial of service vulnerability we found with H.264 Forge. So let's dive into the fun world of the video attack surface. The threat model that we're working under is an adversary crafting a malicious video and getting the videos to play on a victim device. This could be accomplished by either putting the video up on a website and having the user play a video or having the system generate a thumbnail, or by sending the video to a victim directly through a messaging app. Once the video arrives at the victim, often in a container format such as MP4, the video decoding pipeline starts with a user application parsing the MP4 metadata. The user application then forwards the encoded bitstream to a kernel driver, which will parse a portion of it to prepare a dedicated hardware for decoding. This dedicated hardware receives the rest of the encoded bitstream and produces the individual frames that we see. The reason that we have this dedicated hardware is because decoding is a computationally heavy process, so this hardware ensures smooth video playback. So with this hardware video decoder is controlled by a kernel driver, which takes untrusted input from the internet, parses part of the video in the kernel, and then sends the rest to hardware to produce frames. Surely nothing can go wrong here. Before I explain what can go wrong, let me first introduce the basics of H.264. H.264 was standardized in 2003 by the ITU and the Moving Picture Experts Group, or MPEG. And because of these two groups, it has two different names, H.264 and AVC, but we just use H.264 for simplicity. And the spec itself is over 800 pages describing how to decode a video, or essentially going from a compressed bitstream to the frames that we see. And we chose H.264 because it's supported on practically all modern devices. So now I'll give a high-level overview of how codecs achieve video compression. So a video is just a sequence of frames or pictures. And so the main idea to compress videos is to identify similarities within or intra and across or inter frames. Then communication bandwidth is replaced with computation at the endpoint by using prediction. An encoder predicts what an image looks like, then it subtracts the prediction from the original to produce a residue. Then all that is needed to be sent is the prediction instructions and the residue. And in H.264, the prediction instructions and residue are called syntax elements. Looking at the full codec picture, video encoding starts with the originally captured frames. An encoder finds similarities and produces prediction instructions and residue. These eventually end up at a video decoder, which will then follow the instructions to produce the predicted image, apply the residue, and get the final frames. So this is an example of how interprediction works. The current frame sends instructions to look at a portion of the reference frame to copy it over and move it a little bit. For intra-prediction, no reference picture is used. The predicted image is generated, and the residue is applied to produce the final frame. So from a security context, it turns out that unusual prediction instructions can lead to security vulnerabilities in decoders. And here is a collection of previous work showing H.264 decoder vulnerabilities. So how can we produce videos with unusual prediction instructions? Here's a screenshot from the H.264 spec showing what syntax elements look like. It turns out that there was no public tool to easily modify syntax elements, so researchers were forced to create their own tools or modify them manually. For example, when investigating an in-the-wild Apple video decoder vulnerability, Natalie Silvanovich of Google Project Zero shared that she had to forge the file bit by bit, and that it was a terrible experience. To show you some of the challenges faced with working with the bitstream representation, here is the opening sequence of USENIX talks found on YouTube, and here's a portion of its bitstream. If we take this 70 here and just increment it by 71, and incremented to 71, we see that this has some cascading decoding error that shows up in subsequent frames as well. And fun fact, if you play this video on different hardware video decoders, you'll get a different output. So in order to improve the process of working with H.264 syntax elements, we introduce H.264. With H.264, we can programmatically edit syntax elements, which are just Python scripts. So previously, modifying syntax elements was a pain. Now it's just a few lines of Python. Looking at H.264 overall, it is a toolkit to manipulate H.264 syntax elements. It is written in over 30,000 lines of Rust and released in open source with the MIT license. What it does is abstract out the bitstream representation so that you don't have to worry about the individual bits that are set. It will parse the encoded bitstream and maintain the syntax elements in memory. At which point, we can programmatically modify them with Python scripts that we call video transforms, as shown previously. In fact, we can ignore an input and instead generate random videos with syntax elements sampled from a provided range. H.264 can then output the encoded bitstream directly or as part of an MP4 container that can be played on any video player. And here we show that we can just pass in the ranges that we want for each syntax element, and then we can also generate videos with fun-looking frames, such as this one. Using H.264's video generation capabilities, we were able to find vulnerabilities in video players, kernel extensions, and hardware. While the details for each of these are in our paper, I only have time today to tell you about one. So now let's look at this CVE 2022-42846, an iOS kernel denial of service. So I left you at this point saying that surely nothing could go wrong. As you may have expected, things can go wrong. We can get a panic at the kernel. This CVE is a denial of service vulnerability from an unexpected state found while accessing the decoded picture buffer, which I will explain in just a bit. It impacts the Apple D5500 kernel extension, which was found in Apple devices with up to A11 SoCs. And this video decode IP was developed by Imagination Technologies. We found this vulnerability using H.264's video generation. Essentially what we did is we created a batch of 100 videos, sent it to the device, and just saw what would happen. This vulnerability is triggerable from video thumbnailing, which is a zero-click attack surface. And it was patched in these iOS and iPadOS versions after we reported it. So the decoded picture buffer, or DPP. Recall that a decoder goes from prediction instructions to recovered video frames. These video frames are stored in what is called the decoded picture buffer, or DPP. When decoding an interpredicted frame, we need a reference picture to produce the final frame. So the decoder gets the reference picture from its DPP. So an issue that may come up is, what if the DPP is empty? Most decoders would just return an error. We found that this is an undefined state in the Apple D5500. After decoding the frame, the Apple D5500 tries to run some operation on its entire DPP. And so now I'll be showing you some reverse engineered lines of code that lead to a denial of service. First, we access the DPP object to get its size and store it in a uint8 type variable. This size is used to calculate an index into the DPP. But because the size is 0, subtracting 1 causes the value to wrap around, giving us 255 for our uint8 index. Later on, the Apple D5500 wants the size again, so it increments the index by 1. But now the new size is stored in a uint32. This means that adding 1 to 255 won't have us wrap around back to 0, but rather we'll set the new size to 256. This becomes an issue once the decoder starts to process the DPP. It creates a uint8 variable I and loops until it is greater than our new size. But I can only be in the range of 0 to 255, meaning it will never reach 256, so we get stuck in an infinite loop. Meanwhile, there's a kernel watchdog that is monitoring communication from the Apple D5500 kext. And after 3 minutes of inactivity, the watchdog responds and triggers a panic, causing the device to reboot. I didn't describe it here, but there are certain syntax element combinations required to reach this state, which we can just set with an H.264 forge transform. So to summarize this vulnerability, what we've seen, when decoding an interpredicted frame with an empty DPB, a type error leads to an unsatisfiable comparison and thus an infinite loop. This infinite loop causes a watchdog timeout and the device to reboot. This is triggerable from video thumbnailing, which is a zero-click attack surface, and you can imagine you could create something like a video ping of death, where you DOS someone by constantly sending them this video. And we can use H.264 forge to generate the proof of concept. So to conclude, H.264 forge is a domain-specific tool for producing specially crafted H.264 videos, reducing the burden for security researchers exploring the codec space. With it, we found and reported issues in applications, kernel drivers, and hardware, which we describe in our paper. The tool is open source and freely available if you want to start playing with it. I'll now take any questions. Thanks.